Okay, so it's 2, so we're going to start with number 3 today. The first topic is basically a review of what we covered last week because I know some of you guys were kind of confused. So I wanted to go over the last part that we covered, which was finding inverses and solving a system of modular equations. Okay, so we have this review problem here. 17x is congruent to 1 mod 23 and 13x is congruent to 3 mod 21. So first thing we want to do is isolate the x's on both of the equations. So in order to do that, we're going to have to find the inverse. We're going to have to find the inverse of 17 mod 23 because we want to make it to be x is congruent to something and then mod 23. So in order to do this, we're going to have to use the Euclidean algorithm. So 23 equals 17 times 1 plus 6, and then 17 equals 6 times 2 plus 5. Oh, by the way, let me know if you forgot what the Euclidean algorithm was. I'll explain it again. And then 6 equals 5 times 1 plus 1. And since we got our GCD, which is 1, we isolate our 1 over here. So we start the process in finding the inverse. So 1 equals 6 minus 5 times 1. And then now we replace this 5 in here. So this equals 6 minus 17 minus 6 times 2 times 1 because we replaced whatever 5 was there. And then finally we gotta expand this and combine the like terms. So we have 6 times 3 plus 17 times negative 1. This is just me expanding out here and then combining the like terms. And then we got to replace this 6 with this 6. So to do that, we have 23 minus 17 times 3 plus 17 times negative 1. And then expanding and combining, we get 23 times 3 plus 17 times negative 4. And then finally, we can take both sides mod 23, which was our last step in finding the inverse. So after we take both sides mod 23, we get 1 is congruent to 17 times negative 4 mod 23. And then that means that the inverse of 17 mod 23 is equal to negative 4 or congruent to negative 4. So this way we can multiply both sides. Since we had the original equation with 17x is congruent to 1 mod 23. That was the original equation. We can multiply both sides by negative 4 and we get 17 times negative 4. X is congruent to negative 4 mod 23. And since we know this is going to be congruent to 1, so we just get x is congruent to negative 4 mod 23. Yes, I can scroll up a little. So this top part was where we did our Euclidean algorithm aspect. And then the bottom part here was where we actually found the equation, the eventual equation to get us our inverse here. And then after taking mod 23 of both sides, we got that the inverse was negative 4. So then we multiplied both sides of the equation by negative 4 to isolate x is congruent to negative 4 mod 23. So that's what we got for the first part of our equation. So now we got to isolate x for the second part of the equation. And it's basically the same process, but with 13x and 21 instead. So I'm just going to do that again, basically. So this is our first equation. Now we need to try to find the second one. So the second equation was 13x is congruent to 3 mod 21. And we do the same thing. We start with the Euclidean algorithm. 21 equals 13 times 1 plus 8. 13 equals 8 times 1 plus 5. 8 equals 5 times 1 plus 3. 5 equals 3 times 1 plus 2. And finally, 3 equals 2 times 1 plus 1. So now we're done with our Euclidean algorithm, and we have our 1 here. So now we have to isolate this 1. All right, so 1 equals 3 minus 2 times 1. So let's replace this 2 with this 2. So we get 3 minus 5 minus 3 times 1 times 1. And so expanding and combining like terms, we get 5 times -1 plus 3 times 2. So now we can replace this 5 with, oh, sorry, no, not the 5. We replace this 3 with this 3. We just go up on the remainders. So now we replace that 3 with that circled 3. So what we get is 5 times -1 plus 8 minus 5 times 2. So now we expand and combine like terms, and we get 8 times 2 plus 5 times -3. Oh, give me 1 second. Okay, so then now let's look at our other remainder, which is here 5. And then we replace that 5 with this 5. So we get 8 times 2. Yeah, I know this is a tedious process, but plus 13 minus 8 minus 3. Then expand. I'm just going to do this. And finally, one more time, we replace the 8 over here. Okay, we're finally done. So now we take mod 21 of both sides, and we get 13 times -8 is congruent to 1 mod 21. So that means our inverse is -8. Okay. Our second equation was 13x is congruent to 3 mod 21. That was our second equation in the original problem. As you can see up here, 13x is congruent to 3 mod 21. So now we have to multiply both sides by -8. So we get 13 times -8x is congruent to -24. So we know that this is 1 because -8 is the inverse, and we get x is congruent to -24 mod 21. And that is also equivalent to -3 mod 21. And as we can see from the earlier equation over here that we got, x is congruent to -4. We have to combine these two equations. So x is congruent to -4 mod 23, and x is congruent to -3 mod 21. So we solved for this system of modular equations now, finally. Okay, this is not as bad of a process. So we take the first equation and we rewrite it into x equals 21p minus 3, because we know that the remainder when you divide x by 21 is going to be 3. So -3 is the remainder, and p is the result, the quotient. So now we replace this into equation number 2. So we get 2p minus 3 is congruent to -4 mod 23. Keep in mind, all we're doing is just replacing this into here. So now let's simplify. 2p is congruent to -1 mod 23. And, oh no, sorry, mod 23. Okay, so now we just have to multiply, we have to multiply both sides here by the inverse of 2 mod 23. And we don't actually have to, wait, what? 21. Wait, what? What do you mean 21p? Okay. 20, yeah, you're right, sorry, there, yeah, you're right, okay. So 21p is congruent to -1 mod 23. All right, so we can rewrite 21 as -2 because that way it's much easier. -2p is congruent to -1, and so that means 2p is congruent to 1. And then we multiply both sides by the inverse of 2 mod 23, and it's pretty easy to tell that it's 12 just by trying out the numbers. So we'll multiply both sides by 12, and we get And we get P is congruent to 12 mod 23. So we originally had that X is equal to 21P minus 3. So if we plug this in, we should get X is equal to 249. And then by the Chinese remainder theorem, it's going to be mod 21 times 23. So our final answer is going to be X is, Our final answer is X is congruent to 249 mod 483. Finally. So after all that bash, we got our answer. And sometimes problems, it will just require you to bash through them and be patient. And this is when you need to make sure you don't make any stupid mistakes, and try not to miss some part of the problem just because like you have to bash a lot. So that was just a review of last week's problem So if you guys have any questions, feel free to ask it in the chat or the Q&A. So now we have another review problem, but I'm not going to do this one. This is way too, this one is way too bashy. I'll show you guys what the equations are going to be, but you guys can bash that for homework. Go ahead and read it. All right, so let's let the 4 consecutive positive integers be x, x plus 1, x plus 2, and x plus 3. So what we get from the first condition is that x is congruent to 0 mod 5 because x is a multiple of 5. And then the second number, which is x plus 1, is a multiple of 7. The third condition, x plus 2 is congruent to 0 mod 9. And then last condition, x plus 3 is congruent to 0 mod 11. So after we simplify each one of these by isolating the x's, we get x is congruent to 0 mod 5, x is congruent to negative 1 mod 7, x is congruent to negative 2 mod 9, and finally x is congruent to negative 3 mod 11. So this way you're going to have to solve this entire system of equations, and I'm not going to bash that through. You guys can do that for homework. But basically, use the same method that I used earlier by finding x in terms of another variable p, and then plugging in each p into the next equation so that you get the final equation in terms of the Chinese remainder theorem at the end. So that's the first review question. And the second review question, well, technically the third, but here it's prove the Chinese remainder theorem for 2 equations. And what that means is we have 2 equations, x is congruent to a mod m, and x is congruent to b mod n. And by the Chinese remainder theorem, it states that there is a unique value for x mod mn if the GCD of m and n is 1. So this is what I covered last week. So I'm going to show you guys the proof for 2 equations because it's not as complicated as for a bigger number of equations. All right, so let's get started. So what we know from the first equation here is that x is equal to mk plus a, where k is the quotient and a is the remainder. And then let's plug in this into the second equation. So we've got mk plus a is congruent to b mod n. This way we can isolate mk equals b minus a mod n. And because m and n are relatively prime, we know that m has an inverse mod n. So if we multiply both sides by the inverse mod n, we would get a unique solution for k. So let's pretend we multiply both sides by the inverse of m mod n. So we got a unique solution k, let's say it's congruent to c mod n. And now we can rewrite this part because as as an equation instead of a modular equation, k is equal to nj plus c, where j is the quotient and c is the remainder. All right, now we can plug in k back into our original equation for x, which was up here. So we plug in k into here. So let's do that. X equals m times nj plus c plus a. All right, so now let's actually, before expanding this, let's go ahead and take both sides mod mn, because that's our eventual mod. Oops, that's the mod that we will get using the Chinese remainder theorem. So x is congruent to mnj plus mc plus a. This is just me expanding this out. And if we're taking this mod mn, we know that this disappears, right? Because it's going to be 0. So x is congruent to, mc plus a, mod mn. So that's actually essentially our proof. Our proof shows that given this will be our solution, mod in x of x mod mn. And this is a unique solution, which is why the Chinese remainder theorem works. Basically shows you that x can be written as a unique residue, which is mc plus a, in the mod of mn. Does anyone have any questions about this proof? And proofs usually don't really come up that much. It's just nice to know how you get such theorems so that you can remember them better. So if anyone has any questions, feel free to ask in the chat or in the Q&A. If no one has any questions, I'm going to move on to the real stuff that we're talking about today. Oh yeah, I messed up that part. X is not congruent to 0. Okay, so Euler's phi function, or phi, whatever, however you want to say it, but so it says that for a positive integer n, the phi of n is equal to the number of positive integers p such that p is less than n and the GCD of p of n is 1. That sounds kind of complicated, but it's really not that complicated. Phi of n just finds the number of integers less than n that is relatively prime to n. So what that means is, let's say I have the integer 6. Phi of 6 will include the numbers 1, not 2, not 3, not 4, will include 5. So the phi of 6 will just be 2, because there's only 2 integers less than 6 that are relatively prime to 6. So that's basically the phi function. It's a way for you to find the number of integers less than a certain number that are relatively prime to that number. And you may be wondering what the formula for this is. It's actually pretty complicated. So let's say I want to find phi of a prime number. Well, a prime number is all of the numbers less than the prime number will be relatively prime to the prime number. That's basically an aspect of prime numbers, because the only factors of a prime number are itself and the prime number. So let's say we're looking at the prime number 5, right? 1, 2, 3, and 4, none of those have any common factors with 5 except for 1. So that means the phi of 5 will be 4. Phi of 11 will be 10. Phi of 13 will be 12, and so on. So basically for any prime number, phi of that prime number will be p minus 1. So let's look at, this is case 1, by the way. In case 2, let's look at phi of a prime number raised to a power. So p raised to a certain power e. So we know that the only numbers that are going to be relatively prime, that are going to share a factor with p to the power of e, are going to be numbers that have p as a factor. So for example, if we have 5 squared, or no, not, let's say we have 32, which is 2 to the power of 5. The only numbers that are going to share a factor with 2 to the power of 5 are going to be all the numbers that have 2 as a factor. So all the even numbers, basically. So how do we find p of e? So we'll just do complementary counting. we take p of e, and then we subtract all of the numbers that less than p to the power of e that have p as a factor. So how many numbers have p as a factor? It's just all the multiples of p, right? So we have 1p, 2p, 3p, all the way up to p to the power of e. So the number of numbers that have a factor of p in it are going to be p to the power of e divided by p. And we can rewrite this as, we can actually take out p to the e. We get 1 minus p. So that's our formula for phi of a prime number taken to a positive power. So our next case is going to be when we have two prime numbers multiplied together. So phi of p1, actually we'll just do p and q. Phi of pq, where p and q are both prime numbers. This is very important. Make sure that they're both prime numbers. All right, so this follows a similar case as case 2, except we know that now we can't include any of the numbers that are a multiple of p or are a multiple of q. So we have to do complementary counting again. PQ minus all the numbers that have a factor, all the numbers that are a multiple of p. So divide by p, subtract all the numbers that are a multiple of q. And since we double counted, we have to add all the numbers that are a multiple of pq, which is 1. Okay, I know that looks that's kind of hard to see, but it's just pq minus q minus p plus.
Give us a second, everyone. We're experiencing some technical difficulties. Also, I think she purposely froze her camera so she could try to escape. So don't worry, we'll be back when my minions fix this. Oh, if you guys want a poll, sure, I can make a poll for you guys if you guys really want a poll. All right, I'll go make one right now while we wait for Stephanie to come back. Oh. And it takes some time to make a poll, so give us some time, please.
All right, sorry guys. I think my Wi-Fi broke for 2 seconds. Anyway, hold on. All right, so wait, give me 1 second. Technological difficulties. All right, okay, so as we were saying, PQ times 1 minus 1 over P times 1 minus 1 over Q is going to be phi of PQ. All right, so we have one last case. And that last case is going to be phi of P to the power of M times Q to the power of N, where P and Q are both prime numbers. Well, I'm not going to actually work this out, but it's basically the same idea as case 3, but this time it's going to be equal to PM Qn times 1 minus P times 1 minus Q. 1 minus 1 over Q, sorry, that's what I meant. So based off of this, we can see that we can generalize based off of this right here, that given some number n, and let's say we prime factorize n, right? We get P1, E1, P2, E2, up to PM, En, where all the P's are prime numbers and all the e's are exponents. So what we generalize this into is going to be 5n. Oh, by the way, this is all based on equation number 4. We're going to generalize this to be n times 1 minus 1 over p1 times 1 minus 1 over p2 all the way up to multiplied by 1 minus 1 over p to the m. So we just multiply the whole entire number by each one of the primes, taking the reciprocal, and then 1 minus that. So that's how we get the phi function. Yeah, I told you guys it's kind of complicated, but when you're actually evaluating phi, there's a really nice like shortcut. And let me show you guys an example of evaluating phi. So let's say we want to evaluate phi of 120. Actually, no, I have examples. Yeah, let's do this. Phi of 120. So first thing we want to do is, obviously, we want to prime factorize 120. And we get 2 cubed times 3 times 5. So instead of plugging this into this huge annoying equation, we can use, we still plug it in, but it's computation-wise, it's a lot easier. So what we do is we take the exponent, 3, 1, and 1. We take the exponent, right? And we do the same exact number, except we add 1 to each exponent and multiply them all together. Oops. And then times 5 to the 1 plus 1. So basically that's what we did. And then, oh, wait, what do you mean which? Oh, this equation, yeah, sure. Here we go. So we take the n and then multiply by 1 minus 1 over p to the e for all of the different p's. All right, so this method that I'm showing you guys is actually a much better way to compute the phi function. So as I was saying, you add 1 to each of the exponents, multiply them together, and then look at each one of these bases, 2, 3, and 5, and then subtract 1 from each of them and multiply them together, times 2 minus 1, times 3 minus 1, times 5 minus 1. And this way, you can just easily compute it to be 16 times, oh no, sorry, I messed this part up. It's not add 1, it's subtract 1. Yeah, that's my fault. So instead of adding 1, you subtract 1. So 3 minus 1, 1 minus 1, 5 minus 1. My bad. Anyway, you take each one of these exponents, you subtract 1, and then multiply them all together. Then you take all the bases and subtract 1 and multiply them all together. So it's going to be equal to 4 times 1 times 1 times 1 times 2 times 4. And this will be equal to 32. And that is our answer for phi of 120. Okay. So here are some properties that are important to know. Well, actually, the most important properties of the phi function are just the 4 that I listed right here. I'll rewrite them in case it's kind of hard to see. So the first property you should know is that phi of a prime number p is equal to p minus 1. Second property is that phi of p times phi, times phi of q, where p and q are both, phi of pq, where p and q are both prime, that equals phi of p times phi of q. And then the last thing is, for the third property you should know, is phi of p to the power of n is equal to p to the n times 1 minus 1 over p. So these are the 3 main properties that you should know for the phi function, and also how to compute it. So if you guys don't have any questions, I'm going to go ahead and move to the first phi function question. And it's pretty simple. We just need to compute phi of 100. So phi of 100, first things first, obviously we prime factorize. 100 equals 2 squared times 5 squared. And then, as I showed you guys earlier, you take the exponent, subtract 1 from each of them, and then multiply them all together. 2 to the 2 minus 1 times 5 to the 2 minus 1. And then you take the bases, subtract 1, and multiply them all together. So there we have 2 times 5 times 1 times 4. And we get 40, which is our answer. Okay, that is our first phi function. Second is also pretty straightforward. It's just another computing one, but we need a prime factorize 1728. And if you guys don't know, 1728 is just 12 cubed. So that would be 2 squared times 3, all taken to the third power. And that would be 2 to the 6 times 3 cubed. And if we take phi of that, then we subtract 1 from each of the exponents, 6 minus 1 times 3 to the 3 minus 1, and then multiply the bases, but subtracted by 1. And then we've got 32 times 9 times 1 times 2, and that gives us 576 as our answer. All right, so that is how basically the algorithm itself is not that hard. It's just, I just wanted to show you guys how we got the equation and the algorithm. So if you have any questions, go ahead and ask, because the next questions are going to be harder, I think. Yeah, the next topic is definitely going to be harder. Euler's Totient Theorem and Ma Sota Theorem. So these are two of the most important theorems in more advanced number theory, and we're going to be covering them today. So Euler's Totient Theorem states that given any two positive integers a and n that are relatively prime to each other, we have a to the power of phi of n is congruent to 1 mod n. Yeah, this is pretty self-explanatory. I'm not going to prove it today because the proof is kind of difficult, but you should know the theorem. And then for Ma Sota Theorem is just a generalization, well, it's a corollary kind of to that theorem, because look at this, p minus 1 and p has to be prime. So phi of a prime number is always p. What do you want me to re-explain? Which part? How to get the totient or Euler's totient function? The second one. So for Ma Sota Theorem. Okay, you know, I'll just explain this entire page again. So what this thing is saying is, given these two positive integers, and we have GCD of a and n is equal to 1, that just means a and n are relatively prime. They don't share any factors. So then you take a to the power of phi of n. Phi of n, remember, is what we just did. And then you take this mod n. That means a to the power of 5 n is congruent to 1 mod n. I'll show you guys some examples in a few seconds. So that's Euler's totient, right? But now let's look at Ma Sota Theorem. It's basically a specific example of Euler's totient. So instead of having any number n as the mod, we have the mod of a prime number, which is p. And from Euler's totient, remember, we take a to the totient of p. Well, if p is a prime number, and as I said in the previous page, the totient of a prime number is equal to p minus 1. So that's how we got Ma Sota Theorem. For example, for Ma Sota Theorem, let's say we have a is 2 and p is 5. Well, a to the power of 4, that's going to be 2 to the power of 4, which is 16. And 16 mod 5 is going to be 1. Yeah, that's how you do. That's Euler's totient and Fermat's. Let me know if y'all have any questions or if I need to re-explain any part of this. Okay, I'm assuming we don't have any questions. Let's move on to the first Ma Sota Theorem / Euler's totient question. Can I go down? Yeah, I can go down. Here? You mean this part? Okay. If you don't understand this part as well, yeah, okay, no problem. Let me move on to the next problem then. So 2 to the 35 mod 7. There's no way we're gonna actually go and compute 2 to the 35. So let's use a theorem that I just covered, Fermat's or Euler's Toshin, yeah. So by Fermat's little theorem, since 7 is prime, we use that. So that means 2 to the power of 6, we know is going to be congruent to 1 mod 7. And then let's take, since 35 is equal to 6 times 5 plus 5, let's go ahead and take both sides to the power of 5. So 2 to the 6 to the power of 5, congruent to 1 mod 7. So 2 to the 30 is congruent to 1 mod 7. So we're still 2 to the power of 5 off. So let's multiply both sides by 2 to the power of 5. So 2 to the power of 35 is going to be congruent to 2 to the power of 5, which is equal to 32 mod 7. So now we just know, we just have to compute 32 mod 7 and 32 mod, what was that? Sorry. 32 mod 7 is going to be 4. So that means 2 to the 35 is congruent to 4 mod 7. Does this make sense? This is a simple application of Fermat's little theorem. So let me know if you guys have questions about this. And one more thing I want to note about this question is, alternatively, you can use a different approach, which was doing, well, you can use a different approach because we're trying to find 2 to the 35, right? We can do 2 cubed minus 1 to the power of 30. Oh wait, no, sorry. We could also do 2 cubed is congruent to 1 mod 7 because 2 cubed is 8, and then just take to the power of 10, etc. It's basically the same concept, but I just wanted to show you guys how to use Fermat's little theorem in a problem. All right, let's move on to the next one. This one is definitely a bit harder, so go ahead and read it. Actually, you know what? Since this problem is definitely harder than the third and the fourth problems, I'm going to do those two first. So let's do number 3 first. And we just need to solve the congruence x to the power of 103 is congruent to 4 mod 11. Well, we know that 11 is prime, so we don't need to worry about any of the relatively prime stuff. So by Fermat's little theorem, we have x to the power of 10 is congruent to 1 mod 11. And since we have this, we can just take both sides to the power of 10. We get x to the 100 is congruent to, is congruent to 1 mod 11. So now we have to multiply both sides by x to the power of 3. So x to the power of 103 is congruent to x to the power of 3. And we know that from the problem, it says that x to the 103 is congruent to 4. So we know that this is congruent to 4 mod 11. And now we will just have to go through all of the residues of 11 and find which one x would be. So let's start. Let's have a little chart here, x and x cubed. So let's do 1, obviously is going to be 1. 2 is going to be 8, so that 3 is going to be 27. And in mod 11, that's 5. 4 is going to be 64. And in mod 11, that's 9. And 5 is going to be 125, sorry. 125 mod 11 is 4, which is perfect. So that means x is congruent to 5 mod 11, which is what the problem was asking for. So let me know if you have any questions about this. Okay, looks like there's no questions, so I'm going to move on to the fourth problem. We're coming back to the second one after I solve this one. All right, so find the last two digits of 3 to the power of 1,000. As you guys know, finding the last two digits is the same thing as finding something mod 100. So the problem is essentially asking us to find 3 to the power of 1,000 mod 100. And since we see that 100 is not prime, we cannot use Fermat's little theorem. Instead, we have to use Euler's Totient Theorem. So we got to find the totient of 100. I know I found this earlier in a previous problem, A equals 40. From that previous problem number, yeah, you guys can find it. Anyway, we know that from Euler's totient, we know that 3 to the power of the totient of 100 equals 3 to the power of 40, which is congruent to a 1 mod 100. And we're trying to find 3 to the 1,000. But if you notice, then you will realize that 1,000 is actually a multiple of 40. Believe it or not. Anyway, let's take both sides to the power of 25. And we get 3 to the power of 1,000 is congruent to 1 to the power of 25, which is obviously still equal to 1. Mod 100. So now we know that the last two digits are going to be 0, 1. Does this make sense? Oh, do you want me to explain the Fermat's little theorem? Yeah, sure, I will explain that again. Here. So do you guys understand the Totient theorem? Okay, I will explain the Totient theorem again. Oh, well, do y'all understand how to get the totient? Well, yeah, I'll just briefly explain it one more time, okay? For Edward. So basically the totient finds the number, let's say you're trying to find the totient of a number n. Basically what you need to do is you find the number of integers positive integers less than n that are relatively prime to n. And the way you do that is you prime factorize, subtract 1 from each of the exponents, multiply them together. You know, I'll show you, okay. Let's do phi 100 again. So that would be phi of 2 squared times 5 squared, because we prime factorized 100. So we subtract 1 from each of the exponents and multiply them together. And then we also subtract 1 from each of the bases and multiply them together. So then after that, we just evaluate and it gets 40. That's how you find the totient. Oh wait, yeah, the cut 0 is phi. That's the function. I think I just explained it. The phi of a number is the number of integers, positive integers less than that number that are relatively prime to it. You know what? If you're confused, just rewatch the recording once it comes out. Because I explained this earlier. Just watch the recording for that part again, because we need to move on to here. This problem. Yeah, just watch the recording because I explained it all earlier. All right, so let's move on to this problem. A1 is equal to 7. Yeah, just read it. And then we need to find A100 mod 7. So let's work on a few of the terms. So A1 is equal to 7, and A2 is equal to 4 to the power of A1, and 4 to the power of A1. Oh, this is just designed for AMC10 prep or AMC8, but it's mostly AMC10. 4 to the power of 7. And then A3 is going to be 4 to the power of A2, which is 4 to the power of 4 to the power of 7. And we can see that as we get on to the later terms, a to the 100, it's going to be 4 to the 4 to the all the way up to the 7 with a total of 99 fours. Okay, well now we have to evaluate a sub 100 mod 7. So we need to find 4 to the power of 4 all the way up to last 4 and last 7 mod 100. So let's use the Totient Theorem because 100 is not prime. So the Toshin of 100, as I just showed y'all earlier, is 40. But all that tells us, oh wait, did I? Hold on. Yeah, okay, so all that tells us is that 4 to the power of 40, wait, no, sorry. So why am I doing 100? I'm sorry guys, I meant 7. I meant 7 here, not 100. Because that's what the problem is asking. My bad. Anyway, we use Fermat's little theorem, and we do 4 to the power of 6 is congruent to 1 mod 7. And then we need to multiply or take both sides to a certain power so that we can get this monstrosity on the left side. So we need to do 6x plus y equals 4 to the, that thing, so that we can take both sides over here by x and then multiply both sides by 4 to the power of y. I'll show you guys what I mean. I'll show you guys what I mean if that's confusing. So first thing, we want to find y. And let's just take both sides mod 6. So we get y is congruent to 4 to the 4 up to a certain number of 4s mod 6. And let's just see how can we simplify this. We have 4 to the 1 is congruent to 4 mod 6. 4 to the power of 2 is congruent to 4 mod 6. 4 to the power of 3 is congruent to 4 mod 6. So you can see a pattern, obviously. 4 taken to any power is going to be congruent to 4 mod 6. So that means we have y is congruent to 4 mod 6. And from earlier, we had that 4 to the power of 6 is congruent to 1 mod 7 from Fermat's little theorem. So let's take both sides by a certain number x, but we don't really care what it is, and then multiply by 4 to the y, because we know that 6x plus y is going to be equal to 4 to the power of 4 to the, the monstrosity. Anyway, this will be congruent to whatever a100 mod 7, and we know that 4 to the power of y is going to be 4, so basically a100 will just be congruent to 4 to the power of 4, and that will be 256, which is congruent to 4 mod 7. All right, does that make sense? Yes? Good. Okay, cool. I thought that was going to be a harder... Oh, yeah, I'll go ahead and scroll up. Oops. All right, if it sort of makes sense, just think about it. Hopefully it will make sense. Anyway, we have to move on to our last topic. This one is not as difficult, in my opinion, as the topics that we covered today. So yeah, it's called Wilson's theorem. On the packet, I think I already wrote down what Wilson's theorem is. Basically, we have a prime number p. Wilson's theorem tells us that p minus 1 factorial is going to be congruent to -1 mod p. Well, yeah, that's pretty self-explanatory. I'm not going to prove it, but if you guys want to know the proof, you can always feel free to message me and then I'll show you. So let's move on to the first problem. Oh yeah, thank you, Kevin. Anyway, let's move on to the first problem. Go ahead and read it. Yes, P is always prime. What I was saying, in all of the things that I talked about today, P is prime. No, I can't hear you, Edward. You guys are all muted. Anyway, go ahead and read this. Stop. Okay, so hopefully you guys had some time to read this problem. What you want to do is first, let's multiply both sides by 23 factorial. Oh, sorry, that was my dad and my brother. All right, anyway, let's move 23 factorial to the left side. And multiply this out. So let's expand this. So this is equal to A as well. And we want to find the remainder when A is divided by 13. So let's take mod 13 of both sides. All right, but pay attention to one thing. 23 factorial has 13 as a factor in it because it's 1 times 2 times 13 times 14 all the way up to 23. So this will be congruent to 0 mod 13. Same for this, also 0. Same for this, also 0. The only term in this long addition equation, what do you mean? Is that a 5 or a 3? These are all 3s because it's 23. Yeah, I'm writing with like a stylus, so it's kind of hard to write. But anyway, the only term that won't have 0 mod 13 is going to be the one where we actually divide out the 13, which is this term. Because the 13 is going to be gone from this top part. So we don't have 13 as a factor, so it's not going to be 0. But the rest of the terms are all going to be 0, so we don't have to worry about them. So essentially, we're just trying to find this mod 13. And in order to do this, let's think about what the terms are going to be. It's going to be 1 times 2 all the way up to 12. You skip 13, 14 times 15 all the way up to 23. All right, does this part look familiar? It's actually 12 factorial. And by Wilson's theorem, it states that 12 factorial is going to be congruent to 1. And then this part, let's go ahead and simplify this. 14 is congruent to 1 mod 13, 15 is 2, etc. up to 23 is 10. And this part, there's not really a good way to simplify this, but this equals 40320. And then if you divide it out, oh, sorry, sorry, negative 1 over here, not 1. I meant negative 1. Anyway, 40320 mod 13. It's going to be negative 7, if I did my math right. So let's multiply the 12 factorial. We multiply the 12 factorial term, which is negative 1, and then by negative 7, and we get 7 mod 13, which is our answer. Does this make sense? No, I did not make mop. Yeah, that's basically how you get 7 as our answer. So that's basically all the problems that I have for today. Let me know which part you want me to go over. Okay, I think someone mentioned, wait, 40320, yeah, you're right. Okay, yeah, I'm sorry guys. 40320 is 8 factorial. Anyway, find 10 factorial and then take mod 13. 362880. Yeah, I messed that part up. Anyway, that's basically how you solve that problem. I'll go over the Totient Theorem and Flt because I think some of y'all were confused about that. Basically, we have for any A, you take it to the totient of n, whatever that is, and you're trying to find it mod n, that will be congruent to 1. And since I showed you guys earlier from here, I showed y'all that one of the most important properties of the phi function that you need to know is this one, where phi of p is p minus 1, where p is a prime number. Using that knowledge, we do, let's say instead of it being some arbitrary n, we have it to be phi of a prime number. And based on the thing that I just showed you guys earlier, we have a to the p minus 1 is congruent to 1. And that is how you get for Ma Sota theorem. So yeah. Okay, do you guys have any other questions or things that you want me to go over? All right, then I guess today's class is done. You guys can go rest and then join us for Rich's class at 3 o'clock.